Finally, the third of the non-isolated converters that I would like to share with you is the buck boost converter. In the buck boost converter, the switch is in series with the input voltage as we had in the buck converter. Then the inductor is in the middle towards ground. And as you can see already from the direction in the inductor current, it will get magnetized when the switch is closed. Now, as the inductor current has to flow somewhere when the switch is opened and the diode pointing from the anode to the cathode, from the right-hand side to the left-hand side in the diagram, means that the capacitor is getting charged the positive way this way around, so from bottom to top, which means with respect to the input voltage, we're going to get a negative output voltage on the output. Now the voltage is positive as I have defined the positive potential of the arrow down here and the negative potential up here. But some people would also define it the other way around. So positive is always on the top, and you would then get a negative potential with respect to that ground. Finally, the output current is also flowing the other direction through the resistor as we had in the buck and in the boost converter. For the operating states during the switch being turned on, so from 0 all the way to the duty cycle times the period time t, we are magnetizing the inductor current from the input DC voltage source. As the switch is closed and the current can flow in this circuit here. The diode is open as it is getting pulled towards a positive voltage on the input here, and that potential, as we figured out already, is negative with respect to our ground down here. That means the right-hand side of the circuit is taking care of itself, and the capacitor supplies the load with the charges, which generate the output current and therefore give power to the load. In the equivalent circuit diagram, we have the opening of the diode here and the short of the MOSFET there, and therefore we can redraw the inductor in parallel with the input voltage source, and the capacitor and the resistor stay hardwired and in parallel as they have been up in the original diagram. Opening the switch here leaves the input voltage source floating and not contributing to the operation of the circuit, while the inductor current supplies charges to both the capacitor, charging the output capacitors in this direction, and also supplying the load current over to the load resistor RL. The return path of both of those currents go through the diode and therefore forward biasing the diode. That means the diode is conducting and can be ideally modeled as a short circuit. That puts all three of the passive components, the inductor and the capacitor, in parallel with each other. Note that the directions of the inductor current and the capacitor voltage are vice versa, whereas the directions of the load current and the capacitor voltage are the same. Finally, we can again apply the averaging method that we have looked into both in the buck and the boost converter during the on state of the transistor, and we can apply it during the off state of the transistor. First of all, Kirchhoff's voltage law across the inductor dictates that the input voltage is applied across the inductor. During the off state, the inductor is antiparallel to the capacitor. That means the capacitor voltage is negatively applied across the inductor. Similar to that, the output current is flowing negatively through the capacitor during the on state of the transistor, and during the off state of the transistor, the bottom node of the capacitor is defined by Kirchhoff's current law, with the inductor current flowing into it, the capacitor current flowing out of it, as well as the output current flowing out of it, We have seen that scenario already, both in the buck and the boost converter, which then finally relates into the capacitor current being the inductor current minus the output current. Using all of these insights and averaging it across a period, that means weighting the on-state voltage across the inductor with the on-state amount of time and the off-state voltage across the inductor with the respective 1 minus duty cycle times the period t. We require the inductor average voltage to be 0 across one period. Similarly, the capacitor average current across one period has to be 0, otherwise we would be in trouble with that capacitor. During the on state, so from 0 until the duty cycle, we have minus the output current flowing through the capacitor, and during the off state of the switch, we have the inductor current minus the output current as the current flow in the capacitor. Now rewriting those equations gives us the DC transfer function of a buck boost converter, where the output voltage divided by the input voltage is D over 1 minus the duty cycle, and the inductor current divided by the output current is 1 over 1 minus the duty cycle. Now we know this equation already from the boost converter and have looked at how that graphically looks like. The only difference here is that the voltage transfer function is once more multiplied by the duty cycle, and that means it is stretched down to 0. So a duty cycle of 0 gives us 0 output voltage. At a duty cycle of 0.5, the voltage across the capacitor is equal to the input voltage, and at the end, towards a duty cycle approaching 1, theoretically, again, the transfer function would go towards infinity. We have the same practical limitations as we have spoken about during the boost converter. So the validity of that diagram stops at a duty cycle of about 0.7, 0.8-ish. And the realistic transfer function would be limited by the voltage drops across the inductor and the diode. And finally, the energy transfer to the capacitor could not happen anymore, as the inductor is getting magnetized all the time and has no time anymore to transfer the charges from its current to the output capacitor. Therefore, the output capacitor will fully discharge, and the assumption that we have a steady state voltage across the capacitor would not be valid anymore. Now, once again, assuming an efficiency of a buck boost converter to be 100%, which is a pretty fair assumption, we can rewrite the input current using the voltage transfer functions V out divided by V in to be the same transfer function d over 1 minus d times the output current into the equation 57 here. Now reusing also the transfer function from the output current to the inductor current from the last slide and applying the mathematical modification to it, adding a minus d and a plus d in the numerator, we can rewrite that equation into a 1 plus the transfer function d over 1 minus d, where the last fraction is exactly the input current out here, and the number 1 represents the output current. So that means that the final inductor current is the sum of the input current and the output current, which is a major disadvantage for a buck boost converter, as the current rating of that inductor needs to carry both the average input current and the average output current, and that means that the inductors in buck boost converters are getting rather bulky. Exactly as a buck converter and a boost converter, a buck boost converter can operate in continuous conduction mode or in boundary conduction mode, Where these equations are all valid, and the boundary conduction mode again can also be called critical conduction mode sometimes, depending on which textbook you look into. Furthermore, there is the discontinuous conduction mode, which means that the inductor current returns to zero before the period is actually over. And in this operation mode, the equations are not valid. We're going to have a look at the operation of a buck-boost converter in discontinuous conduction mode very soon in this course.